Hello, my name is Payton Fortuna in Chemistry 213, taught by Professor Ben Hui. This is my presentation on the Mukaiyama-Aldol reaction. To begin with, I'll start with a discussion about a general Aldol reaction. An Aldol reaction involves an aldehyde or a ketone and reacts with the alpha carbon with a carbonyl of another molecule to form a beta hydroxyaldehyde or ketone. In other words, the reaction forms a beta hydroxy carbonyl compound from two carbonyl compounds by making a carbon-carbon bond. For example, this is an Aldol reaction under basic conditions. The solvent is hydroxide, and the first step, illustrated by blue arrow 1, is an electrophilic attack of a hydrogen atom by the hydroxide, forcing the electrons in the hydrogen bond onto the carbon atom, forming a carbocation. Next, the negatively charged carbon forms a double bond between carbon 1 and carbon 2, illustrated by the green arrow, forcing the pi bond between carbon 2 and the oxygen atom to break, creating a negatively charged oxygen atom. The new product is then forced to react with another aldehyde, with a double bond between carbons attacking the alpha carbon and forcing a pi bond to break between the carbon and the oxygen, as illustrated by the purple arrows, beginning the process of forming the carbon-carbon bond between the aldehydes. This illustrates one issue in these reactions, known as self-condensation, where an aldehyde is forced to act both like a nucleophile and an electrophile during a reaction. The newly formed product reacts with water to neutralize the negative charge in the oxygen atom, as illustrated by the arrows in blue, to give a beta hydroxyaldehyde. Aldol reactions are important, as the products are often found in naturally occurring molecules in pharmaceuticals, such as the heart disease drug known as Lipitor, which, when initially created by Pfizer in 1996, used two Aldol reactions in its creation. Typically, Aldol reactions are conducted using a Bronsted base or acid as the promoter in protic solvents. Bronsted bases and acids involve the transfer of protons, so their usage leads to unwanted reactions, such as dehydration and, as discussed above, self-condensation. Also, they suffer from limitations due to regiochemistry issues. In the early 1970s, an organic chemist named Teruaki Mukaiyama was researching boron-mediated aldol reactions while also looking at organic reactions involving titanium 4 chloride, as he believed the titanium 4 chloride would make the carbonyl carbon atom more electrophilic so that it could react with a weak nucleophile. He began to focus on using Cl-enol ethers, which are mild neutral nucleophiles that react well with good electrophiles and carbocations. Cl-enol ethers, or SEEs for short, are prepped from ketones and are quite stable and can be isolated via distillation. In 1973, a group of researchers in Japan, led by Teruaki Mukaiyama, discovered a cross-aldol reaction involving Cl-enol ethers, which reacted with aldehydes in presence of Lewis acid titanium 4 chloride. This reaction provided a good yield of product, and since the SEE was prepared via ketones, it was regioselective, which eliminated the issues of regiochemistry in the earlier attempts at aldol reactions. This is the mechanism of the Mukaiyama-Aldol reaction between an aldehyde and Cl-enol ether, with titanium 4 chloride acting as the Lewis acid. So the first step of the mechanism is for the Cl-enol ether to proceed with a nucleophilic attack with the double bond at the carbon of the carbonyl group. This forces a pi bond between the carbon and oxygen to break, allowing the oxygen to form a bond with the titanium 4 chloride. Next, the lone pair on the oxygen of the ether forms a double bond with the carbon. The subsequent product is formed, as shown. Then, the bond between the titanium and the oxygen breaks, allowing a lone pair to attack the positively charged oxygen on the right, as demonstrated, causing the Cl methyl to detach before reattaching to the oxygen. The subsequent product is formed, a beta hydroxy carbonyl compound. This reaction was an important discovery, providing an example of aldehydes and ketones being activated by a Lewis acid in the presence of a carbon nucleophile, and helped significantly increase the utility of aldol reactions. This helped pave the way for other reactions, such as the hetero-Diels-Alder reaction of Danishevsky's DN, which is a cycloaddition reaction involving a compound known as Danishevsky's DN, a very electron-rich reagent, leading to dihydropurones, which are used for tobacco smoke identification. The Mukaiyama-Aldol reaction was an important discovery, as it led the way for other cross-aldol reactions to be discovered. Additionally, it solved, quote, the significant challenge to selectively synthesize one desired stereodefined aldol product out of the many possible alternative aldol products, thanks to the usage of Lewis acid to accept the lone pair to make the carbonyl group have an overall formal positive charge, allowing an easier reaction with a weak nucleophile and elimination of potential unwanted side reactions. This brings me to the end of my presentation. To end with, my name is Payton Fortuna, and this has been my video project on the Mukaiyama-Aldol reaction.